let's look at the MCR for all the loading condition and different boundary condition cases. So far, we covered some MCR against the simple beam subjected to end moment M0. In that case, we calculate MOCR, right? Then how about for these the different loading cases? So this case can be calculated MOCR times CB. It is called MCR. Then what is CB? CB can be calculated is this equation. The maximum moment and this moment gradient. And M1 is 1/3 point here. M2 is midpoint here. M3 is another 1/3 point here. If you input these values here, you can calculate CB. Then you can get the MCR. How about the MCR for the boundary condition? This is the simply supported case. So we consider this boundary condition here, and this one. Okay, this boundary condition. Due to this boundary condition, this beam cannot rotate like that at this support. This displacement here and then moment here at both ends equal 0. Okay, moment means 2 prime, right? That is the boundary condition. In that case, we can get very standard MCR. Okay, MCR equals CB MOCR. In this case, CB equal 1. So that is very typical MOCR. How about the cantilever beam? In this cantilever beam, moment applied here, then it deformed like that. And then this is real part. If you consider the imaginary part, so from here to here is 2L. So from this MOCR, the standard equation is KL instead of L. KL instead of L. This is hinge to hinge distance, like a column. Do you remember the column case? So this is K equal 2. That is MCR. How about the fixed end beam case? This point is inflection point. It looks like hinge, moment equal 0. So the distance from hinge to hinge is 0.5 L. So K equal 0.5. Right? 0.5. So if you input here, then you can get MCR. If you look at the cantilever beam with end load and distributed load, you see this is cantilever beam. This one is end concentric load. This is distributed load. Okay? You have load at the span. In that case, your MCR can be written like that. But K value here can be obtained from table 5.4. 5.4 is this one. Left hand side is a fixed. Right hand side is a free end. For top range loading case 1.4 L. All other cases 0.5 L. If right hand side the boundary like that, it is supported but hinge supported, then top range case 1.5 L, or other case 0.7 L. Top and bottom flange is supported by hinge, then 0.6 L, 0.6 L, like that. If you input those values, then you can get that one. How about the fixed end beam with concentric load and distributed load? Okay, MCR equal PCR L over 8. Okay, MCR equal omega L square over 12, right? Here, CBS can be calculated A times B. A divided by B. For bottom flange load, A for shear center load, A divided B for upper flange load. So A and B can be obtained by table 5.5. So CBS consider some boundary condition as well as moment shape, moment gradient. By the way, CBA can be obtained by table 5.5. Let's look at 5.5. Distributed loading case A and B. Concentric loading case and midspan A and P. Let's look at this one. This one is the continuous beam with lateral support. Continuous beam means if we see the top view, then we have the lateral support and both end and midspan. Inside the view, we have end moment M0. If we see only side view is simply supported, but if you see the top view in relation with lateral torsional buckling, it looks like continuous beam. Do you understand? So in the case, the MOCR standard equation. So here, if you see lateral torsional buckling shape like that, this hinge to hinge distance is L over 2. So that means your K value is 0.5. So if you input 0.5, you can get that equation. Now let's look at the continuous beam with lateral support with concentrate load, uniform load. This case is end moment. This case is lateral load at the span. So here, side view is this one, simply supported case. Top view is you have lateral support, both end and mid length. In that case, your MCR equal CBS MOCR. You know MOCR? Then what is CBS? CBS is A times B for bottom, A for center, A divided B for top. So CBS consider the boundary condition regarding lateral torsional buckling and moment gradient. AB can be referring table 5.10, this one. In distribute case, this is A, this is B. Concentric load case, this is A, B equal 1. Top view is this one. And let's look at the design equation. AISC LRFT standard provide some design equation. Vertical axis is flexural strength. That means lateral torsional buckling strength. Horizontal axis is embrace length. So this flexural strength divided by 3 range. Plastic yielding, inelastic buckling, elastic buckling. If your embrace length is less than MP, the beam fails by plastic yielding. Embrace length is somewhere here and inelastic buckling case. This range is elastic buckling case. I think many of you knows the embrace length because you already learned in that undergraduate study. If I draw this on for someone who doesn't know regarding embrace length, support vertically here. Embrace length is related to lateral support here. If you have a lateral support at this 2 point, then this is your LB, okay? Embrace length. If you have the lateral support here again, then this is your embrace length. Do you understand? So embrace length is distance between lateral support. Let's look at LP. LP, LR, those equations are provided standard. If you think about local buckling is related to width thickness ratio. This is a flange. Flange width thickness ratio is less than 65 over square root Fi. Then there is no local buckling. In the wave case, wave height, wave thickness ratio is less than 640 divided by square root Fi. Then there is no local buckling. So the section that has this kind of some condition is called compact section. If the section is compact, we can consider only lateral torsional buckling. So LB is less than LP, then plastic yielding case. So your Mn equal MP equal Fij. If LB is between LP and LR, it is inelastic buckling case. So the equation can be written like this because they are some linear equation. Straight line. You can written this form. You already learned in undergraduate course, right? Still design course. This times CB. This resulting value must be less than MP. Maximum the capacity of any beam cannot be greater than MP. So you have to check MP because you multiply CB here, sometimes this calculated value is greater than MP. In that case, you have to use MP. So if you see here, if you multiply CB and your equation goes up like that due to CB like that. Then if you LB, somewhere here, then you calculate Mn is this one. It is greater than MP. Then your moment capacity is not this one, this one. The maximum moment capacity cannot be larger than MP. So this is MP. If CB is, for example, 2.3, in that case, this kind of case can occur, okay? If CB equal 1.0, that is this equation, this curve. If LB is greater than LR, the elastic buckling case, that is this equation. So you must be familiar with this equation. So far we cover elastic buckling cases, right? These equations, okay, different boundary condition, different loading cases like that. We cover elastic buckling cases. Then how about inelastic buckling cases? In order to get some value in elastic buckling cases, we have to use numerical integration using computer. So LRFD standard provide this practical design equations. Let's consider lateral support. Let's consider this case. This compression flange is embedded this concrete slab. That means concrete slab provides some lateral support against lateral torsional buckling, continuously supported. So in that case, your LB equal 0, right? How about this case? This beam, this concrete connected by this shear stud. If assuming shear stud distance is 30 centimeter, then your umbrace length is 30 centimeter, right? So 30 centimeter umbrace length is very short. This the MN must be MP, failed by yield, rather than lateral torsional buckling. How about this case? This girdle is this one. Some transverse beam is this one. So this transverse beam provide lateral support on this girdle. In that case, umbrace length is LB, LB, LB. Also, channel can provide lateral support. Now, look at design example. This beam subjected to end moment M0. Determine moment capacity using LRFT. W16 by 36 is a wide flange section. Provide the elastic modulus and then shear modulus, every property. Umbrace length is 150 inch in this case. So let's check the compact section. Flange with thickness ratio is less than that limitation. Web height to thickness ratio less than the limitation. So the section is compact. So let's calculate LP and LR. This is LP. This is LR by standard equation. Umbrace length is 115 inch is 12.5 feet. So your umbrace length is between LP and LR, 6.3, 18.3, this range. That means this beam failed by inelastic buckling. Then you have to calculate inelastic buckling. Mn equals CB, MP, MP, MR, yeah, this equation, right? So this is a uniform moment, uniform end moment. Your CB equal 1. Plastic moment equal this one. MR equal SX minus FY minus FR. FR is residual stresses. So this one, you know all these values. Okay, you can calculate Mn. So it is nominal moment capacity. If you apply the resistance factor 0.9, you can get design moment capacity. I cover up to design example. I'd like to explain MR. MR equal Sx Fy minus Fr. Okay, that is residual stresses. I think the students who already took the undergraduate course, I explained this MR in detail in undergraduate courses. But I think some of you didn't take my course in undergraduate, so I'd like to explain this equation MR. MR is this one. Then moment is divided by this line. Okay, so the moment divided by inelastic buckling or elastic buckling. Now this line above is inelastic buckling, down is elastic buckling. This edge section has residual stresses. If I draw here like that, this residual stresses. If I draw here, tip part is compressible residual stresses. This is Fy. So let's say this Fy equal 0.3 Fy. In that case, the stress due to the moment is, let's say, 0.7 Fy. Then if you add together, that is Fy. So here, this one is the section modulus. If this value is 0.7 Fy and Ss. If your moment is this value, then your developed stress due to your moment equal 0.7 Fy. And your existing residual stresses already, that is 0.3 Fy. We plus together, then it yield, right? Fy. So it become yield from this tip part. It is that point. So that is MR. Goodbye, everybody.